Hello and welcome to Toddcast number 44, continuing on with alkene reactions. Toddcast 40 through 43 have started the introduction, terminology like Markovnikov and anti-Markovnikov, syn versus anti-addition. And so to date, we've done a lot of alkene reactions, and now we're going to shift into we're going to do more alkene reactions, but now it's a matter of getting more organized and trying to see the bigger picture utility in synthetic pathways, how to synthesize one molecule from another. But with that in mind, a couple more reactions. So I'm going to start with something called halogenation. And stereospecific reaction means we'll get very specific stereoisomers and ads in a certain way. And just a quick review, Markovnikov versus anti-Markovnikov is regioselectivity. That is a determination of which of the atoms involved in reaction go to which of the two carbons on the alkene. And then stereo selectivity, stereospecific addition that we're doing here, involves which side do these atoms attack the alkene from. So it's always important to remember that alkenes are planar in nature. So I'm going to draw this structure just briefly with my p orbitals. And then an H. And so we always have to make a decision. We're reacting two BRs, those are going on. So if they add at the same time, then it'll extend out and I'll have that structure, which apparently this is anti, not syn. So they can't be adding at the same time. So it ends up, they must be adding one at a time. So one will go on first, and then the second one will come on second. And so we'll learn how this happens along the way. But syn versus anti-addition really is simple as if they add at the same time, it's got to be syn because they're adding simultaneously from the same phase. And if they add one at a time, then once one goes on, it makes that side more crowded than the other. And so they add opposite one another. Okay, so let me clear my picture and start into this. So 1Br goes on first to form what they call a bromonium ion bridge. So we'll go into that mechanism, how that works. It's similar to the mercury acetate that we used in oxymercuration. The second one adds from the opposite side of the bridge because once you add one bromine on, it makes one side more crowded. So the second Br goes from the less crowded opposite side. Okay, regioselectivity, we're adding the same atom, Br and Br, to each carbon. So there is none to speak of. And then stereoselectivity, anti-addition. So that's going to lead to whatever chirality or chiral centers we get, but it's an anti-addition. I have shown it up, down, up on left, down on the right, but it could just as easily be down on left, up on the right. And that's one of the things we're going to make a big deal about. So whether it's up, down, or down, up, those be known as enantiomers because both chiral centers differ. Okay, so the halogenation mechanism. This is how it's happening. Bromine is more electronegative than carbon, so we're going to treat it as the atom that wants to receive electrons. The pi bond, as we've learned, pi bonds are a little bit weaker than sigma bonds, so we treat them like an available electron pair. They're not quite as available as, let's say, a lone pair, but they still are available, so it can come out and attack the Br. Either Br is fine. You can choose one's closer, and then kick out the electrons to the other Br. So at first, we get the carbocation with the bromine attached, and then a free bromide ion floating around in solution. Just like the mercury was able to, and mercury acetate was able to donate its electron density, or coordinate it, I should say. It's not going to fully donate, form a bond, but it's going to coordinate. And when it does, you get this coordinated species. So again, a dashed line is coordinated as opposed to a fully bonded atom. We consider the bromine to be closer to the less crowded side. So notice if I drew a straight line down the middle here, Br is a little bit closer to the secondary than tertiary carbon. So this is our intermediate. It's known as a bromonium ion bridge. Bromonium because it's overall a positively charged compound. Bromine is taking the brunt of most of that positive charge. And this bridge, we just call it, remember we can call it a bridge just because that's the name they assigned to it. So the second BR is not going to come in this side because it's already blocked. So it's going to come in from the opposite side. And because this bromine is bonded more to this carbon than this carbon, you have a slight delta plus here. The second bromide in is going to prefer the positively charged side. Okay, one of the subtleties that I didn't bring up in this mechanism, but it was shown there, is this works best if we have a completely nonpolar aprotic solvent. So carbon tetrachloride is the solvent we use, so that way the bromine has complete control over where that plus charge is distributed. If you do it in a polar protic solvent, as we'll learn, then that solvent can also coordinate the plus charge, and that can create havoc or just sort of create a different situation, different substitution situation. And so for this one, we're going to have this formation of this bromine coming in, breaking that out. So that one goes up, that one goes down. But had the bridge formed on top, so had I put the BR attacking on top, I had it up here and coming down, so the bridge on top, then it would have been, instead of up, down, would have been down, up. Okay, so let's go into a little more detail here. Before adding this reaction, a little more detail is that I should say this forms plus enantiomer. I'm just going to write enant, mostly because I didn't plan my space very well. And so if my, there's no chiral center here, this one has a chiral center, but the up-down will be, the enantiomer of that would be the down-up. So in this case, there is only one chiral center, which still makes it an enantiomer, but not up-down and down-up. It's not that the up-down of this one is necessarily a chiral center. Okay, so as mentioned, CCl4, get this, but the interesting thing is if you do it in a protic solvent, something nucleophilic, it ends up water is a better nucleophile than the Br minus. Water actually goes on and you end up deprotonating it. So it's shown in the final stage for the OH, but you end up getting H2O attacking on that other side from the bromine ion. And then we can also do the same thing with CO2. Notice it's chloroform, a little bit different solvent. I don't think it's that big a deal, but just note of interest. And again, each of these are plus enantiomer. And for some of you, you probably have a professor that emphasized that you had to write plus enantiomer. You could draw out the enantiomer or you can write it. So that's pretty standard for chemists. We like you to show all the stereochemistry. Okay, so that's our stereospecific anti-addition. So one more to add to our spider chart. Our spider chart so far has 4 on this one and 1 on the other one, the 2 spider charts we're making simultaneously. So let's go ahead and add our Br2 in. So our Br2 in water is going to form the OH and the Br as such. Notice they are enantiomers of one another. And then also want to do Cl2, and I could have easily done Br2. I'm doing it in ether this time. Again, the solvent's going to vary depending on the alkene. Not going to get too hung up on the solvent, but it's an aprotic solvent, so therefore it's going to be the Cls that go on. So I did CHCl3 in the example on the previous page. This one just going to do ether. Cl up down versus, oh my, uh-oh. So that is that first one. So the second one has to be the exact opposite. Oh, it is. Never mind. My eyes bugged out on me. So the CLs are anti to one another. So it is fine. I do apologize for that. Okay, so spider chart. We're complete here. We have room for 2 more. So let's get those reactions. A molecule known as MCPBA, you'll memorize it, but I want you to know more specifically, it's known as a peroxybenzoic acid. So a peroxy acid, so peroxide is this. That's a peroxide, if you recall. And an acid is this. So combine the two. A peroxy acid has features of both RC double bond O and then an OOH. Highly unstable, like a peroxide, that means highly reactive. The R happens to be a benzene ring with a chlorine on it. So metachloroperoxybenzoic acid. The key thing I care about is peroxy acid. So that species, you're going to see us in class using different variations of this. But note that instead of being RCO2H, this is now O3H. So peroxy acids have an extra O. They're hot, strong oxidizing agents. That extra O is going to be shared. We'll go into the mechanism of it. But what I hope you do, I'm going to erase everything now. What I hope you do is immediately notice these are adding anti. So you get the first one and it's an antimer. They're adding anti to one another, but more importantly, if they're anti, that means they're adding one at a time. One goes on, crowds one side, and then you attack from the opposite. So this is going to be kind of like a ripoff of the bromonium ion. And so you're hopefully starting to see a pattern that the mercury adds in a certain way, bromine followed it, this peroxy acid is going to follow it. So if you know the pathway for one, you can kind of, I don't know, have hedge your bets and have a good educated guess for the pathway for other ones that are similar. So mechanistically, we'll look at this in a second. For now, O inserts into the ring to form, just like we talked about the bromonium ion bridge, how it forms that three-membered ring. We also get a three-membered ring here, only this time it's called an epoxide, or also known as an oxyring. And then water, under acidic conditions, will attack, and in doing so, break open that ring, and that ring oxygen becomes an OH on one side, and the water turns into OH on the opposite side. So probably best to look at the mechanism before really delving into those comments. Regional selectivity, you're adding the same thing to both sides, so we don't have any to speak of. But under certain conditions, I want to mention that if you use, let's say, an alcohol instead of water, then you would get OH on one and let's say OR on the other, OCH3, OCH2, CH3, something like that you would have. But for this example, because what we're adding is the same thing that MCPVA is going to put on, we don't see an issue, see it here. Stereoselectivity, anti. Absolutely important that you know that. Okay, so this is what happens when we treat it with water. But if we change it to an alcohol, for instance, so the water, we have an OH on each side, but if we treat it with an alcohol, as I mentioned, then you will get OCH3 here and here. Notice that OCH3 is on the tertiary, or the more substituted side. And so when the epoxide broke, this was free to come in and attack. So you put the OH on first with this one, going to the less crowded side, and the OCH3 comes on second. This is something you just see over and over and over. It's really no different than the BR or the mercury acetate mechanism, but we still look at it as something unique. Mechanistically, so here is our peroxybenzoic acid with the carbonyl and an OOH. I put this O in red because it is our oxidative one. It's one that's going to ultimately leave and reduce the peroxy acid back down to an acid. It's going to interact with double bond. Double bond is going to go up to get the O. Simultaneously, O is going to push electron density into the pi bond. To do that, it's going to have to take electron density back. So we're going to have this weird starting point of the carbonyl is going to reach out and pick up the H, which frees those electrons to attack, which puts too many bonds to O, which then pushes it back over. So this triggers this attack to that carbon. So we now have a bond from the red O to this carbon. It breaks the pi bond, which then can attack the O. But now that O has 1, 2, 3 bonds, one to each carbon and one to the O. So it needs to break that bond. And in doing so, it needs to come all the way back and replace that bond over there. So a lot going on. I expect you to know the coordinated positioning of everything. if you were actually taking my class, but you do not have to necessarily um, go into too much detail on the intermediates at this level. Future OChem classes definitely, but this one, just know the basic flow of everything. So this O is the one that's being inserted in. Okay, so I want to actually get rid of uh, like this pi bond kind of was already broken, so this arrow is unnecessary. So I want to get rid of that one. And just say that'll do it for the bonds we need. Okay, so we have this O inserted. This is a strained three-membered ring, so it's highly reactive. It's going to get protonated. When it does, it can break open and form a carbocation, but a plus charge on O is going to actually, well, it depending on the resonance. This could move over and leave plus charge here. This could kick in. And it's not resonance because it's a sigma bond, but it's how strong this bond is open to debate. So just like we've seen in the other cases where we have that bond kind of being a coordinated bond more than a full bond, we can still think of it that same way. So the next molecule then, considering this is going to carry a bigger partial plus than this, it's going to attack the bigger partial plus side, which kicks this bond out. Once again, notice we have the exact same situation, a three-membered ring, where one side is a weaker bond than the other, that gets readily broken. So just like the other cases, you're getting anti-addition. This water is going to get deprotonated and turn into the OH. So this is going to come off. I should draw a solvent coming in of some sort. In all likelihood, it's probably water. If the solvent comes in, we'll pick up that H. In doing so, leaves behind the two OHs. Again, it could have attacked from the top as well. I drew the bottom simply because I'm lazy and I cut and paste into other pictures that I had. But you're not lazy like me. You're going to draw both potential mechanisms, both intermediates, to make note that up, down, or down, up can all form. So I don't want to say this is complicated from this point forward because it's the same thing we saw before, but this can prove a little bit tricky. Definitely want to color coordinate your arrows and your bonds to figure out where things start and finish. Spider chart time. So one more to add, MCPVA or peroxy acid. When we treat this with that, we're going to put in the presence of acidic water, we're going to put OHs, and we're going to do it in an anti-fashion. So our stereochemistry is anti. So you get both of those in antimers. So one more spot. So done for now. Next podcast, we'll complete that spider chart and start into our next one. So hope it's going well. These are going by pretty fast, but the more you do them, the more I hope that just you get used to the style, get used to this mechanism. So hopefully this was good, and I will see you at the next podcast. Bye.